Okay, welcome to my introduction to networking or my fundamentals to networking, depending on which course you're in. In this chapter, we are looking at specifically chapter 6, the network layer. And part of this chapter deals with explaining how the network layer protocols and its services support communication, how it deals with end-to-end communication, whether it be small or medium businesses, determine the appropriate devices to route traffic, and well as configure a router with basic configuration. A big part of this is we're looking at more of the network layer and dealing with like header information as well. So we're going to break this chapter up into four main categories: the layer protocols, routing, routers, and a basic router config. And we're going to end with a summary. First part is our network layer protocol, and this is the OSI layer 3 network layer. This layer provides services to allow end device or end node communication across the network. And part of this process is the addressing for end devices, the encapsulation, the path selection between point A and point B, and then the decapsulation. At this layer, we focus on two main categories. We focus on our IP, and that is our logical addressing scheme. There are two major types, IPv4 and IPv6. Older protocols could be like IPX, AppleTalk, CLSNS, NetBIOS, things like that. So the IP components have two major portions. It has an IP header and a segment. The IP header is what we're dealing with. A segment is the segmentation PDU from our layer 4. IP packets flow through the inner network. Normally they are connectionless, meaning there is no connection established before sending of the packets. They're best effort, and they are media independent. So, if the sender doesn't know that a letter is sent, then it doesn't get it. If the receiver is present, if the letter arrives, if the receiver can read the letter, then the sender doesn't know. It's best effort. I send it. If you grade it, if you get it, great. If you don't, oh well. Here's another great example. Packets are routed through the network very quickly, and they may take different paths, and there could be loss because of the quickness of the transmission, and so some of that data could be lost because of it. There are mechanisms in place to prevent this, but right now there could be loss. It's media independent, so it can go over copper or fiber or wireless. It doesn't matter. The encapsulation portion is, again, it takes a transport layer PDU, which we call a segment, and we pack on an IP header to it. Then it becomes a layer 3 PDU or packet. Versus if we are looking at a layer 4 PDU, it's going to be data with segment wrapped around it. The important thing is understanding that at layer 3, it takes the layer 4 PDU and puts an IP header on it. So what's an IP header look like? So there's many types of IPv headers. Here's an IPv4 packet header, and it deals with things like its version, its length, its differential service, the length, maybe a time to live, protocols, checksums, source and destination, some padding, altogether roughly 20 bytes of information. Again, not everything is going to be used, but they all play a role in the IPv4 arena. So now, how do we actually view it? If you get Wireshark or something similar to Wireshark, you can actually see the breakdown here, that the version, the source, the destination, the header length, the differential service, the identification, the flags, time to live. So you can actually decode the header. Some limitations are address depletion, internet routable or routing tables and their expansion, as well as the lack of end-to-end connectivity, meaning one end to the other end without any type of private or natting or masking of addresses isn't quite there yet. With IPv6, we have an increased address space, 2 to the power of 128. Okay, so before we talk about that, for IPv4, it's 2 to the power of 32. That's roughly 4 billion-ish addresses. With IPv6, we have 2 to the power of 128, which is 340 undecillion. So it removes the need for NAT. It helps simplify our packet handling and headers. It drastically increases our address space. And because it's newer, it actually helps build in some integrated security. So now let's look at a simplified IPv header. So IPv4 versus IPv6. You'll notice IPv6 header, it's a lot different. It only deals with the version, traffic class, flow label, payload, next hop, hop limit, source and destination. So there are some commonalities between the two, but not all of them. The IPv6 header is drastically simplified. So again, we break this up into 4 byte sections, and our version and traffic class, all of this can be decoded from a packet capture. And here we have our IPv version 6 header, where it lists our version, our traffic class, our flow label, our payload. I mean, everything that we need. Moving on is our routing. So the question with routing is, what is the purpose? The purpose of routing is how to make forwarding decisions based off of that layer 3 logical address. For example, if we are dealing with just a local area connection, then we don't have to go to a router. But if we want to send something outside of our network, we need to have a router so that that router can make the path selection outward. So what we have to have is like an exit point or an egress point. And in a modern network, we call that a default gateway. And that default gateway is just the IP address of the router that's on our LAN. All of this information allows us to make the best path selection. So again, that default gateway must maintain their own local routing table to ensure that the network layer packets are directed to the correct destination. So we make tables like direct connection, local network, and local default routes. Our network destinations could be as simple as, if we're not sure where to send it, we send it out our gateway. If it is a local network, we send it to ourselves. Here it is with the 000 network. So any network with any subnet mask, we can send it out our gateway of 192.168.10.1. That way, if we're not sure where to send it to, we can always send it to our router or our default gateway, and it will make that decision. Sample IPv6, same thing, except here we are doing it in hexadecimal with IPv6 addresses. So directly connected networks. On a LAN, you know what you're directly connected to. If we are using an example, like if we have a person holding hands, you know who you're holding hands with. You know who you're connected to directly. And here, R1 is directly connected to 3 networks. It's holding hands with 3 people. It happens to share a hand with R2. So it knows about R2, but it doesn't know about the remote networks coming off of R2 because we're holding hands with R2, but R2 is also holding hands with someone else. Here is our basic routing table so that we can see where we can start learning about other networks. For example, if we want to see where 10.1.10/24 is, that's actually learned here, and it's learned via those interfaces. So it's learned that interface. Just like we know that these networks should be learned by those appropriate interfaces, or because they are directly connected. And my line went horrible through that. So directly connected routing table entries should show the IP address, its slash subnet, directly connected, and what interface. So A identifies how the network was learned by the router, C versus L. So if we go back, we can actually C is connected, L is locally. So this was learned locally. This one was learned because it was connected. B would identify the destination and how it was connected, directly connected. And then the last part is out what interface. So here we have another one. How it was learned, which I believe is EIGRP. The IP address, the administrative distance or the trustworthiness of that network, the metric to reach the remote network, how it was learned. This would identify the next hop. This will let you know the elapsed time to that location and what interface to send it out. That way it can know exactly how to get to where it is going. Again, this is the destination, trustworthiness, the metric used to reach the other network, the next hop, the time it's been up, and the interface to send it out of. Here we go again. It is D, the network, trustworthiness, the metric, next hop, the time, or the interface outbound. This takes a while to start learning to decode. So this is not something that people just lurk once and they know it. Like this takes time to decode. All right, moving on to section 6.3, routers that operate at layer 3. They come in multiple different shapes and sizes. The router has a CPU or processor, or multiple processors depending on size, and it has an operating system. It has things for storage, like RAM and ROM and NV RAM and flash. So the important thing is RAM, it's volatile. It runs the it runs the iOS. I keep wanting to say OSI. It runs the operating system, its running configuration, and it has the tables in memory. ROM, which is non-volatile, are the Bootup instructions, the diagnostic software, and a very limited boot iOS. NVRAM, which is also non-volatile, houses the startup configuration. And then lastly, Flash. Flash holds the operating system and other system files. Inside of a router, we have a power supply. We have a shield for our add-on cards. We have a fan for cooling. We have memory, SD-RAM. We actually have a non-volatile RAM chip, which is number 5. We have a processor. And we have some type of add-on modular card for additional functionality. Here we have an AIM add-on card, which is Advanced Integration Module, which is 7. If we're looking at the front of the router, front subjective, the working side of the router, we will have add-on cards. We'll have a few fixed ports, but we will have some add-on cards. That way we can add the appropriate things that we need. Here we have a WIC2T card. We put nothing in the extra spaces but fillers or blanks, and we added a WIC2T card. This will give us serial, and this will allow us to use our LAN. Our Cisco IOS comes in multiple different flavors, and it handles different things. Our router's specific feature sets could be addressing, interfacing, routing, security, quality of service, or other better resource management depending on the appropriate feature set that we need. Also, what we have is a boot set file sequence. Like, how does it start? First thing, it has to go through some type of power on self tests. Then it has to load its operating system into memory. Maybe load other system files that are related to as well. Then it needs to pull out from NVRAM the startup config. Then allow us to connect to it. There has to be a structure for this. And here it is. You turn the router on. From ROM, it will go through its post and bootstrap. That way it can make sure that it passes power on self-test. Then it will be the bootstrap, which will load the bootstrap. It will then, from Flash, load its operating system. And it may also load information from a TFTP server if required. Then it will load the configuration data. And that can be from whether it be NVRAM or TFTP or console. It will allow us to have a configuration brought into a play. But it has to go through this process first before we get access to it. Next is our different versions. So if we do a show version on any Cisco device, we should get the type of software, the version of software, the date, it's a bootstrap version, where the image file is stored, what features it may have, what interfaces it may have. So that way, if you need to know detailed information, we can grab that. Here we know that we have a Cisco IOS C1900, which is a universal 9M license. It's version 15.24M1. That lets us know that it's stored in Flash, that location. That lets us know what type of device we're working with, as well as some of the licensed features that we have. Lastly, it is configuring a router. We've done basic configuration already, but How do we configure a router again? We're already familiar with basic navigation, how to set up a host name, how to set up passwords. We're already familiar with that. So basic configuration should be like host name, secret passwords, login passwords, service password encryption to encrypt all the passwords, a banner, as well as saving the running config. But how do we actually configure interfaces? We do that by navigating to the appropriate interface. For example, in global configuration mode, if we want to configure the gigabit interface, we would do interface gigabit Ethernet 0/0. That's assuming we want to configure this guy right here. If we wanted to configure the second gigabit interface, we would do what we did before. Interface gigabit 0/1. If we want to configure this guy over here, it'd be interface serial 0/0/0. Three important things when configuring interfaces is first, the IP address. It has to be in dotted decimal form, IP space subnet. Then there is this description command. So just description and then write anything. That way there is a description of what that interface does. And lastly is this no shutdown. That basically says turn on. So now let's talk about how we verify this. If we go to a perfectly exact mode and we do show IP interface brief, it will actually show us our interfaces and if they're assigned an IP address and if they're up or down. This part right here normally means that they are administratively down. We forgot to do the no shutdown command. This one over here normally tells us if they're wired up correctly or not. So a quick recap. If we're dealing with a host on a LAN, we don't need a default gateway. If we're dealing with hosts from different networks, then we need a router because we need that default gateway to do path selection between the two. We can also set default gateways on a switch. That way, the switch knows where to forward the information, just in case. Also, that allows a remote administrator the ability to log into it if you set it up correctly. Like you assign an IP address to the switch. Then you can connect to that IP address on the switch. And that's actually all I had for this chapter. So I wanted to thank you and hope you guys have a great day.